Hello everyone, my name is Wojciech and today I'm going to be talking about the Monte Carlo tree search and how it uses randomness in decision making. So let us start with saying what is a Monte Carlo tree search. And it is a powerful search algorithm that leverages randomness and probabilistic methods to optimize decision making. It is known for application in games like Go or chess and is widely used in fields requiring fast real-time decisions. Most notably, it was used by DeepMind team in programs like AlphaGo and AlphaZero. Let's now look at the definition, what is a tree and what is a game tree. So the tree is a type of graph which is a set of vertices and edges between them, in which each pair of vertices is connected by a unique path. And alternatively, we can just say that a tree is a connected and acyclic graph. And a game tree is used in combinatorial game theory. A game tree is a graph representing all possible game states from a given starting point. And now we can just see on the left we can see a binary tree, which is a typical tree studied in graph theory. And on the right we can see a game tree from the game of tic-tac-toe, in which in each node we can see the possible position on the board that can arise. So what is the main focus of MCTS? The main idea behind Monte Carlo tree search is to find promising moves at each decision point, and by performing rollouts or just random playouts to sample possible outcomes, and those outcomes will guide us later and will tell us how to expand our game tree in an optimal direction. And this is why this algorithm is very interesting, because it builds and searches the tree at the same time. So the way it builds the tree depends on the previous searches that it performed. So let's now go through the steps of Monte Carlo tree search. The first is selection, which is given a starting point. Let's call it root. We select the most promising actions at each time until we hit a node which is not explored yet. Then we have an expansion step, which is if we have a node which haven't been explored yet, we examine all possible actions that can arise from this node. Then we go to some simulation, which is picking one of the actions and just going through a random simulation. And the last step is backpropagation, which is taking the outcome of the simulation and updates scores in each node on the path that connects our root to the last node that we were examining. And the algorithm repeats itself a lot of times, refining its search and improves decision quality until a stopping condition, which is usually a time or iteration limit. So let's talk about the selection step. And in selection step, the algorithm recursively selects nodes until the tree in the tree until reaching a leaf node, a node where simulation has not been conducted yet, and in which the state of the game is not terminal. So now let's talk about how we actually pick one on or other node in each step. So the core challenge is to balance depth search and breadth search in the game tree. So the depth search means exploring promising branches, and the breadth search means examining all the new possibilities. So just for example, the Shannon numbers are the numbers that represent all total possible chess position after each ply. A ply is like a half move. So one move in chess is 2 plies, because the person playing white pieces has to move, and then the player playing dark pieces has to move. So after one ply, obviously we can have 20 possible legal positions on a board. After two plies, 400, because for every one of 20 moves made by the first player, the second player can answer with his own 20 moves. And it grows very rapidly, and we can see that after 10 plies, which is just 5 moves, there are approximately 69 times 10 to the 12 possible game positions, which is so much that modern computers will not be able to calculate it quickly enough. So we can't just do a brief search, because the number of possibilities is just too large. But we have the formula that balances exploration and exploitation, and in this formula, for each node, we take the average score in the node plus c, which is some constant, times the square root of logarithm of the numbers of visit in the parent node divided by the numbers of visit in the current examined node. So if the score is high, then the first part of this formula is really high, but also if the number of visits is very low, then the second part of the formula grows very big, and this with the constant c, we can balance between those two factors. So this is just the example. If we have here the state 0, and we have two actions A1 and A2 that leads to state S1 and S2, using this formula we can calculate the scores, and in this example we can see that the score that is leading to S1 is bigger than the one to S2, so we go to S2, and then the next step, which will be expansion, tell us to generate all the possibilities, pick one at random, and perform a rollout. So now we go to expansion. Expansion, as I just said, is if we have a leaf node, we create a list of all possible actions, say AN, and for each action in this list, we generate a child node, CN, with L as the parent. So in the previous example here, we can see that S1 was the leaf node, then we generated two actions A3 and A4. We generated two nodes that corresponds to these actions, and then we randomly select one of the child nodes and perform the simulation step, which is a random rollout. The one particular thing that is very interesting about this search is that the game tree can be built asymmetrically. So UCT allows us to examine more promising moves more deeply, but also make sure that we don't abandon some nodes completely. So on this picture here we can see that somewhere in the very right of this game tree is some particularly promising move, which then was calculated fairly deeply, but all the other actions were also calculated, just maybe some of them very narrow because they didn't seem particularly promising. So the simulation is that for the selected leaf node, we run a simulation but randomly selecting actions until reaching a terminal state, which is usually for a game like chess, checkmate. And the result of the simulation is then passed back to the propagation step, and the backpropagation step is recursively updating the path from the leaf node to the root by first updating score. So we use a notation inspired from programming languages here. So this plus equal sign means that to the node n we increase the score by s, where s is the simulation result. We increment visit count, so every node on this path from the root to the leaf node is then incremented by 1. And when we do that, we move up the tree. So from n, we go to the parent of n and do the same. And this process enables us to enables Monte Carlo tree search to remember and prioritize successful paths. On the picture, we can just see the visualization of this process. So selection means that if we have already existing nodes, we go from the one to the other by using UCT formula. When we have a node that has been not explored yet, which means that they are actions that weren't used up to this point, then we probably will pick these actions, because then the formula UCT will say that this is most promising move. So this is the expansion step. Then the simulation, which means that default policy here is just a random playout, which means taking random actions up to the terminal state. And when we hit the terminal state, we do backpropagation, so we take the score and we go up the tree and do things that are listed here with the red dots. And the final step of the algorithm is, after the search is complete, we want to know what was the optimal action. And in MCTS, actually, the optimal action that is returned leads to the most visited child node, and not the child node that has the highest average score, for example, because a high average score in a less visited node may simply be due to the lack in a small sample of simulation. Whereas a most visited node, we are guaranteed that this node was examined very, very frequently in the simulation. Here we can see the demonstration of the game tree being built and searched at the same time, and anyone interested can go to the third position in the references to see this website themselves. And here we can see that the game tree is built, but at the same time, with each next iteration, it will update the scores and possibly create more nodes with each next iteration. So why choose MCTS over other algorithms? Well, the first thing is that it does not require domain-specific knowledge. So, for example, in games like Go, chess, and so on, we don't have to have a very advanced evaluation function. We only need a set of rules and a termination condition, and that's all that this algorithm needs to work well. The second thing is that MCTS improves iteratively, refining decisions over quality over time, and it is because it goes through promising moves very often due to the UCT formula. The third thing is effective for vast search spaces, even with asymmetrical, unbalanced search trees. And very, very important thing is that it works in real time, making it suitable for applications such as route optimization in navigation. And again, it is adaptable to complex environments with limited resources due to this, that it does not require domain-specific knowledge again. And those are references for this presentation, so 4 here and 2 additional here, and thank you for your attention.